Let's take a look at an example problem within Module 8. So in this sample problem here, we have example problem 8.2.1, taking a look at the effects of damping. So suppose we're given a system, shown down here in this figure 8.2.3, where they tell us that our mass is m equals 1, and we have a spring constant that is given to us as k is equal to 16. Now they ask us to investigate the free response as we increase the damping for 4 different cases, for c is equal to 0, 4, 8, and 10. Now they also give us the initial conditions to use here, that x of 0 is equal to 1 and x dot of 0 is equal to 0. So we come down here, we have the spring mass damper problem here. We can see we have an external load F of t there and our displacement over here of x. So now we've had a chance to look through the problem statement, understand what they've given us, what they're asking us to solve for. The next thing to do is create our setup page. So label our problem here. We have example problem 8.2.1, effects of damping. We're given that m is equal to 1 for our mass, k is equal to 16 for our spring constant. We have c is equal to 0, 4, 8, and 10 for 4 different cases here. And we're also given our initial conditions of x of 0 is equal to 1 and x dot of 0 is equal to 0. I redraw out my given diagram over here. I can see my spring, my damper, and my mass over here. Now, what do they want us to find? So they want us to find the free response for each of these 4 cases as we increase the dampening from 0 up to 10. So before I begin my solution, the first thing I do is find my key equations. So for my key equations, I can reference back to table 8.2.1 in our textbook. This is the solution forms for the free response, which is what we're looking for, of a second order model here. So I have my general equation right here, given me as x double dot plus ax dot plus bx is equal to 0, where b is not equal to 0. And I have 4 different cases here for what my a's and b's are according to that equation and the corresponding solution forms for all 4 of those. So now I can begin my solution here. I know what they've given me, what they're asking me to solve for. I have an idea for some governing equations for this here. So as I begin my solution, again, I reference back to that same equation here. So this is from 8.2.1 on page 501 of our text if we're looking at the 4th edition. And again, here is our general equation here, mx double dot plus cx dot plus kx is equal to f of t, where for our particular problem here, they give us a k value of 16 and they give us 4 different c values from 0 to 10. So we can solve this, find our characteristic equation here. When we find our characteristic equation, it would be s squared plus cs plus 16 is equal to 0. So this would be a quadratic here, so we could find the roots of the quadratic if a is equal to 1, b is equal to c, and c is equal to 16. I know that's a little bit confusing here using the general terms for quadratic. So we'll just put it right into radical form over here. So using our variables here, our s is equal to negative c plus or minus the square root of c squared minus 4 times 1 times 16 all over 2 times 1. We can reduce this down and simplify, so s is equal to c plus or minus the square root of c squared minus 64 over 2, where we have varying values for c that we can plug in here in order to get our roots if c goes from 0, 4, 8, and 10. So let's just pick the first case here. We'll let c is equal to 0 for the first part of our solution here. So we're looking for free response, so we go back to that table 8.2.1. I've included the table on this slide here as well, so we can quickly reference it. We have our general form, x double dot plus ax dot plus bx is equal to 0, where for our case here, our a is equal to our c value, b is equal to 16. So we plug in here, we have x double dot plus cx dot plus 16x is equal to 0. But this is for a c of 0 for this particular case here. So now this reduces down to x double dot plus 0x dot plus 16x is equal to 0 when we plug in those known values for this problem here. So then what I do is for those a's and b's, from that quadratic, our general quadratic equation here, I can check up top here with our equation here and plug into these 4 different cases. So I plug in the first case here, well, 0 squared is not greater than 4 times 16. Second case, well, a squared 4b, so 0 squared is not equal to 4 times 16. Now a is equal to 0, well that is the case here, and b is greater than 0, so that's true. But just check the fourth case as well. A is equal to 0, no that's not true. So none of the first, case 4, case 2, and case 1 are not true. So we're dealing with case 3 here. So if we go back up top to case 3 here, you see I've circled that. Now this is our solution form over here. That we have x of t is equal to my c1 times the sine omega t plus c2 cosine omega t. So that's why down here now this is my solution from the information that we had from our table 8.2.1. So now with this general solution here, x of t is equal to c1 times the sine of omega t plus c2 times the cosine of omega t. Put my omega value in here. My omega is equal to 4 in this case here for this problem. Plug that in. Now I have x of t is equal to c1 times the sine of 4t plus c2 times the cosine of 4t there. So from this here, now what I'm realizing is I have a c1 and a c2 I need to solve for. Well, I have one equation, two unknowns, but I do have some initial conditions. So plug in my first initial condition here, x of 0 is equal to 1. So with this guy here, I can say, okay, if x of 0 is equal to, plug in my t value of 1, c1 times the sine times 4 of t of 0 there, plus c2 times the cosine of 4 times 0 there. Well, the cosine of 0 is 1, and the sine of 0 is 0, so that term drops away, so I'm left with x of 0 is equal to 0 plus c2. Well, x of 0 for my initial condition is 1, so 1 is equal to c2. So now I have a value for c2. I need to come up now with a value for my c1. So I can use my second initial condition here. X dot of 0 is equal to 0, so I need to take the derivative of this equation up here and then plug 0 in for it. So I do that there. X dot of t is equal to 4 times c1 times the cosine of 4t minus 4 c2 times the sine of 4t there. Then plug in my initial condition at 0. So we have 4 c1 times the cosine of 0 minus 4 c2 times the sine of 0. So again now sine of 0 goes to 0. Cosine of 0 goes to 1 over here. So we're left with 4c1 on the right side of the equation. On the left side, x dot of 0 is our initial condition of 0. So 0 is equal to 4c1, or c1 is equal to 0. So now I have values for c1 and c2. c1 is 0, c2 is 1. So I can go back and plug into this general equation here. X of t is equal to c1 times the sine omega t plus c2 times the cosine of omega t, where my omega is 4, my c1 is now 0, and my c2 is 1. I can plug into that. X of t is equal to 0 times the sine of 4t plus 1 times the cosine of 4t. So I'm left with x of t is equal to the cosine of 4t for my solution when c is equal to 0. So now what we want to do is continue on for our other c values here. So now we can do the same thing when our c is equal to 4. So we go back to our table 8.2.1 over here for our solution for free response. Come up with our general equation here, x double dot plus ax dot plus bx is equal to 0. Go through now for our case here, a is equal to 4 in this case, and our b is equal to 16 in this case here. So we can plug those values into all of these four cases from our table. And when we do that, now is a squared greater than 4b? No, it's not. Is a squared equal to 4b? No, it's not. Is a equal to 0? No, it's not. So it is not equal to 0, and our a squared is less than our 4b. Yes, this is our case here. So you can see I've boxed this in up here. So now I have a form for my general solution up here. I now have that x of t is equal to e to the rt times c1 times the sine of omega t plus c2 cosine omega t over here. So I can go down through, and I can also see I have a expression for my r value, so I can solve out my r. R is equal to negative a over 2, which is equal to negative 4 over 2, or negative 2, so my r is negative 2. Plug into my general solution form down here, so x of t is equal to e to the rt times c1 times the sine omega t plus c2 cosine omega t. Plug in for my r value there. I can reduce it down just a little bit, and we end up with this right here, which then what we want to do for this is go through that same process we did for c is equal to 0 case here and solve for our c1 and our c2 using the initial conditions. Now you can go ahead and do this by hand like we did for c is equal to 0. You could plug it into MATLAB or another numeric solver, and when you do that, what you end up with for our c of equal to 4, we have this expression here now. X of t is equal to 1.5 e to the negative 2t times the sine of the square root of 12t plus 1.047. So now that brings us to our third case here, where our c is equal to 8. So we go back to our general form again, x double dot plus ax dot plus bx is equal to 0. In this case here, a is equal to 8, or b is equal to 16 for this equation here. So I can go down through here. Is a squared greater than 4b? No. So our first case is not there. Our second case here is a squared equal to 4b. Yes, it is 8 squared. 4 times 16, that's the case. A is not equal to 0, and our a squared is not greater than 4b. So our case that we're dealing with is number 2 here. So our general solution here for our form is x of t is equal to c1 times t c2 times e to the s1 t, where if we need our s1, we can go back through our roots equation and plug that in for our s1 value here, based off that quadratic equation we solved at the beginning of this problem there. So that's how we solve for our s1. As far as our c1 and c2, we can solve that the same way based off of our initial conditions. X of 0 is equal to 1, and our x dot of 0 is equal to 0 here. So we can plug in those initial conditions. And what we end up with here is that x of t is equal to 1 plus 4t times e to the negative 4t. So now we can move on to our fourth case here for c is equal to 10. We have our general equation x double dot plus ax dot plus bx is equal to 0. So we'll look through and find that if we go through our 4 cases here for our a is equal to 10 and b is equal to 16 here, what we end up with is we have, it's not case 2, it's not case 3, it's not case 4, but it is case 1 here, where a squared is greater than 4b, and we have distinct real roots of s1 and s2 for this case here, so that's why we're going to go with 1. So our general form of our solution here is x of t is equal to c1 e to the s1t plus c2 e to the s2t for our general solution here. So first thing we want to do is use our quadratic that we had at the beginning of this problem here to solve for our s values here. So we can go through this here, and we have our general form. S is equal to negative c plus or minus the square root of c squared minus 64 over 2. Plug in our value for c, so s is equal to negative 10 plus or minus the square root of negative 10 squared minus 64 over 2, so s is equal to negative 10 plus or minus the square root of 36 over 2, or s is equal to negative 10 plus or minus 6 over 2, so s2 is equal to 8, s2 is equal to 1 for our two values, our two roots for s1 and s2 that we can plug back up into our general solution here. So we rewrite our equation here for x of t. X of t is equal to c1 e to the negative 2t minus c2 e to the negative 8t when we plug in our s1 and s2 values there. So let's go with our first initial condition here. X of 0 is equal to 1. X of 0 is equal to, plug in our time of 0, c1 e to the 0 minus c2 e to the 0. Rearrange this and we end up with is that 1 is equal to c1 minus c2, or c1 is equal to 1 plus c2 there. So in order to use our next initial condition, we need to take the derivative of our expression here. So x dot of t is equal to 8 c2 e to the negative 8t minus 2 c1 e to the negative 2t when we take that derivative. Then we can plug in our next initial condition when time is equal to 0 here. So x dot of 0 is equal to 8 c2 e to the 0 minus 2 c1 e to the 0, or 0 is equal to 8 c2 minus 2 c1. We can rearrange this and manipulate it a little bit. 8 c2 is equal to 2 c1. Then from there we go down here, we can rearrange it slightly more, and we end up with at the bottom here 6 c2 is equal to 2, and c2 is equal to 1/3 once we solve for our c2. So we can take that value, plug back up into this expression now that we have a c2 value, and we can get a c1 expression there. So c1 is equal to 1 plus that 1/3, so c1 is equal to 4/3 there. So now we have c2 is equal to 1/3 and c1 is equal to 4/3 from using our initial conditions. So for c is equal to 10, we go back up to our general expression. X of t is equal to c1 e to the negative 2t minus c2 e to the negative 8t. Plug in our values for c1 and c2, and we do that here. We now have this expression that x of t is equal to 4/3 e to the negative 2t minus 1/3 e to the negative 8t. So that is for all 4 cases. Now we have a solution for c is equal to 0, 4, 8, and 10. So with that, c is equal to 0, we have an expression. C4, we have our solution. C is equal to 8, we have our solution. And C10, we have our solution there. Now we can go through and graph these all in MATLAB. and find out for c is equal to 0, c is equal to 4, c is equal to 8, and c is equal to 10. We could graph all of these different solutions.